elementary school, they told us about the units, or the ones column, which was the 3, and then the tens column was the 8, and then the 5 was the hundreds column, and then the 6 was the thousands column. I'm not sure that I really fully understood that. But what was really meant was what I just put down. And notice that in order to read this number, look how I just read it. The ones column, the 3, then the 8, then the 5, then the 6. So in order to know what that 6 means, you really have to count from right to left. You're really reading numbers like in Arabic and Hebrew from right to left. If you think about it, as I say, to know what that 6 means, you really have to count backwards from the 3, which represents a number of ones, and the 8, which represents a number of tens, and so on. So 5 is the number of 10 squareds, which is 100. Here, 5 times 10 squared. By the way, we won't be doing this because we're dealing only with whole numbers, but I'll just mention, just to help show the unity and consistency of mathematics, I suppose we had the number, say, 204.27. What this really means, again, we won't be dealing with decimals, but look at what's happening here. So look at the whole number part, this. So this is a code for 2 times 10 to the second, that's 2 times 100, plus 0 times 10 to the first, plus 4 times 10 to the 0th, plus 2 times 10 to the negative 1, right? Isn't that how you would read this too? It's 2 tenths. Well, what's 10 to the negative 1? It's 1 over 10, so it's 2 tenths, plus, and the 7 is in the hundredths column. That's really 7 times 10, so it's 7 hundredths. Well, 10 to the negative 2 is 1 over 10 to the positive 2, which is 1 over 100, which is 100th. And so it's 7 hundredths. And notice that when we write numbers, in this form, what does this form mean? It means a sum. So here's the sum, there's the sum you're adding, right? A sum of multiples of powers of 10. 10 to the 3, 10 to the 2, and so on, 10 to the 1, 10 to the 0. We say, from the Greek word for 10, we say the when we write in this form, maybe I should put in the word numbers. When we write numbers, and that's what I'm talking about, numbers, in this form, namely a sum of multiples of powers of 10, so close parentheses there, we say the numbers are written in decimal form, as you know. Or in the scale of 10, and 10 is called the base, or the to use a Latin word, radix, but base is fine. The coefficients such as the 6, 5, 8, 3, over here, the coefficients of the powers of 10, the 6, the 5, the 8, the 3, the coefficients of the powers of 10. I mean, you know all this, but you probably never saw it written out formally. So that's what I'm doing now. I'm just saying something that you, quote, have known for a long time, all this, but I'm being more explicit about it than you probably have seen before. The coefficients of the powers of 10 are called the digits of the number. Now, strictly speaking, I don't know if you've come across this use of the word digit, but your fingers are called digits, 10 digits. So digit actually, like decimal, refers to 10. So strictly speaking, you could say digits refer to the coefficients when you're writing in the scale of 10, when you're writing with 10 as the base. But we will just call the coefficients when we write a number in any base, I'll just call them digits. There are specialized words, for instance, if you use base 2. We'll take a look at that shortly. They're called binary digits, which is abbreviated into bits. You've probably heard that. But I'll just call the numbers that are written in any base, not just 10, I'll call them digits. Coefficients, namely the numbers listed in writing the whole number. So we will call the coefficients, that is the number, make that plural, the numbers listed in writing the entire number, we'll call them digits anyway. So for instance, when we write a number, when the base, I'll call the base B, and the base has to be greater than 1. I mean, if you look up at the top, you're taking a polynomial, you're taking a sum of multiples of powers of the base. But if you used 1 as the base, the powers would all be 1 and you wouldn't get anywhere. So the base will always be more than 1. 1 would not be a suitable base. You can use 10, you can use 2 and have the binary system, or you can use any integer different from greater than 1. So when we write, when the base B is bigger than 1, when we write a number, I guess. When we write a number in a different base greater than 1. So when we write a number when the base b is more than 1, so if the base is 10, we just write the number like over here at the top. You just write the number the way you've always written it since elementary school. But if the base is different from 10, write the number with the base as a subscript. Sub under script writing, subscript. After the number. And read the number by saying the digits separately. And then the base if it's not understood. So for instance, so if this is a number in base 5, and we'll talk more about that, but so instead of the 10s that we have at the top, we'll have powers of 5. So we'll write 5 as a subscript, or some books will show it with parentheses. So either way, but what I'm saying is this number, that 34102, is not 34,102. That's only in the case of base 10. If the base is different from 10, this is read 3, 4, 1, 0, 2, base 5. 11001 base 2 is 11001 base 2. So it's not 11,000. Again, you read and you use the words hundreds, thousands, millions, and so on, only in base 10. If the base is different from 10, you just read the numbers, which I'll call digits, even though they're not base 10 digits. Notice that when we write a number in base 10, as you've known for a long time, but I don't know if you've really thought of it this way, in base 10, you use 10 digits, 0 through 9, and then once you get to 10, you would move it over here and write it as times 10. So in base 10, we use 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we don't go up to 10. If you take a look at the last line that I have written here with base 5, notice all the digits there are less than 5. They could be 0 or 1 or 2 or 3 or 4, because once you get to 5, you are no longer in the units column, like over here. It would be whatever it is, in this case, 0 times 5. So let's write what these actually mean, and then we'll prove a theorem showing that you can always write a number in any base greater than 1. And we'll take positive numbers because, again, a negative number is just -1 times a positive number. So we'll just look at positive numbers. But So how do you convert, change a number written in a different base to decimal form? And again, by decimal, I'm not talking about, maybe you're used to thinking of a decimal as actually having a decimal point like 2.5. No, when I say decimal form, I'm talking about base 10. Well, you read it the same way as we read this number at the top. The reading from right to left, the 3 was the coefficient of 10 to the 0. The 8 was the coefficient of 10 to the 1. The 5, I'm reading from right to left, the 5 was the coefficient of 10 to the 2, and the 6 was the coefficient of 10 to the 3. So as you move from right to left, those become coefficients of increasing powers of 10. Well, the same thing is true in any base. As you read from right to left, the rightmost, again, I'm calling it a digit, the rightmost number, the rightmost digit, is the coefficient of 10 to the 0th, which is just that number. And then the next number to the left is the coefficient of the base, whatever it is, to the first power. The next number to the left is the base to the second power. So let's do that. For instance, here, let's go back to what I have 3 lines above. 3, and again, notice how I'm reading it. It's not 34,000. 3, 4, 1, 0, 2. So base 5. So this is the number of 10 to the 0s. This is the number of 10 to the 1. Not 10s. We're dealing with base 5. The idea is the same, but so the 2 is the number of 5 to the 0s. 0 is the number of 5 to the firsts. The 1 is the number of 5 to the second. 4 is a number of 5 to the third, and the 3 is a number of 5 to the fourths. So again, I'm calling them digits. The digits, just as we had here, up here at the top, the digits are the coefficients of the successive powers of the base. Up here at the top, the base was 10, and then the 6, 5, 8, 3 were the coefficients of the powers of 10, starting with 10 to the 0th over here, and increasing. The next one was 10 to the first over here, and then 10 to the second, 10 to the third. So it's exactly the same thing here. The digits are the multipliers, the coefficients of the powers of, in this case, 5. So this number that I put into parentheses, you don't need the parentheses. So let's look at it. The 3 on the left is the coefficient of 5 to the 4. And the next number to the right, we saw when we counted from right to left, we saw that 4 is the coefficient of 5 to the third. And then the 1 plus 1, that was the coefficient of 5 to the second, plus the next number is 0. So it's 0 times 5 to, there it is, 5 to the first, plus 2. So you don't have to write 5 to the 0th, but for uniformity, I'll write it. So this number would be 5 to the 4th. 5 squared is 25, and squaring that is 625. What's 3 times 625? Is it 1875 maybe? 5 times 625, 5 times, no. 3 times 5 to 3 times 625. 3 times 25 is 75. 3 times 6 is, yeah, I think that's right. Plus, so 5 to the 3rd is 5 times 5 is 25, times 5 is 125, times 4, is that 500? Yeah, 4 times 125. So it's 4 times 100 plus 25. So you use the distributive property. 4 times 100 is 400, plus 4 times 25 is another 100. Okay, so plus 1 times 5 squared is 25, plus 0 times 5 plus 2. So whatever that comes out to be. Let's look at the other number that I have written up here, the 11001 base 2. 11001 base 2. So that 1 refers to the number of 2 to the 0s. That 0 is the number of 2 to the 1s. That 0 is the number of 2 to the 2s. That 1 is the number of 2 to the 3s. And that number is the number of 2 to the 4ths. So this equals 1 times 2 to the 4th plus 1. That's the second one from the left, which is the multiplier of 2 to the 3rd, plus, again, for completeness and to show exactly what's happening, I'll put in the 0. 0 times the next lower power, 2 to the 2nd, plus, and there's another 0 here, which is the coefficient of 2 to the 1, plus 0 times 2 to the 1, plus 1 times 2 to the 0th. So this is 1 times 2 to the 4th. 2 to the 4th is 2 times 2 is 4 times 2 is 8 times 2 is 16. Plus, now we're up to 1 times 2 to the 3, which is 8. Now we have 0 plus 0 plus 1 times 2 to the 0. 2 to the 0th, remember, is not 0, it's 1. So it's plus 1. So this is 25. And again, for emphasis, I'll put in base 10. But if I don't put in the base, it's understood to be base 10. In the scale of 10, the base or the radix is 10. So notice, not surprisingly, if you think about this for a moment, when you use a larger base, you need fewer digits because the number can be built up by a larger base. But when you use a smaller base like 2, well, take a look at this last example we did. In base 10, the number has just 2 digits, whereas in base 2, the number requires 5 digits. So yes, of course, you have a smaller base, so you're going to have more digits. Computers can handle the greater number of digits, and base 2 just does make it simpler in terms of circuits being closed or open. A closed circuit means electricity goes through, and open circuit means it doesn't go through. Right? If you have a closed circuit, the electricity can go through, but if it's not closed, so this is closed, that would conduct electricity. This is open, so it's open at the top, open, electricity would not flow. There's nowhere to go, it gets stuck at the end. So maybe I'll just make a note of what I said. smaller the base, the more digits are required to write a number. And vice versa, the larger the base, the fewer digits are needed. So you have to be careful and see what the base is. For instance, what number is 10? So not 10, it's 10 base 2 is 2. So the way you express 2 in base 2 is a 1 in the 2's column, so to speak, a 1 multiplying 2 to the first, and then 0. So again, 2 meaning 2 base 10, but I don't write the base, it's understood to be 10. Okay, so let's show that in writing a number in base, say, n digits are needed, and those digits are 0, 1, 2, up to and including n minus 1, but not n. So as I said a minute or two ago, in base 10, you use 10 digits, stopping at 10 minus 1, or 9. And so we can express any number using the base number of digits starting with 0 and going up to, but not including the base. So let's show that this can always be done. Any positive integer m can be written uniquely and as usual, that means in exactly one way, sometimes expressed as in one and only one way, in the form m equals a sub n b to the n plus a sub n minus 1 b to the n minus 1 plus etc. So next one will be a to the n minus 2, b to the n minus 2, plus etc. down to a to the 2, b to the 2, plus a to the 1, b, which is b to the 1, plus a sub 0, which is a sub 0 times b to the 0th, where, let me interrupt. For people who are not used to seeing a polynomial written in this form, don't be intimidated by these subscripts. The a sub n at the beginning, where I wrote m equals a sub n is just the coefficient, the numerical coefficient of the nth power of b. And then the next term, a sub n minus 1, that's just the n minus 1 is just to identify it as the coefficient of the n minus 1 power of b. So these a's, the next one, a sub n minus 2, that's just whatever the numerical coefficient of the n minus second power of b is. And going to the right, a sub 2, that's just a number. And to indicate that it's the number that multiplies b to 2, I call it a sub 2. So as I say, don't be intimidated by the subscripts. They have no mathematical content. They're just a matter of notation, where the base or radix b is an integer that is more than 1. Well, as I said before, I mean, if you used 1 as a base, that wouldn't be a suitable base, because if you look at the line just above that, n equals, powers of b, well, you wouldn't be getting anywhere with powers of b. If b were 1, they'd just be 1s. B to any power, 1 to any power would still be, would just be 1. And as I said, the a's are all going to be less than b. So 0 is less than or equal to a sub I, where a sub I is any one of those a's, I'll write it, is necessarily strictly less than b for, so a sub I. So what's I? I is any of the numbers 0, 1, 2, 3, up to n minus 1. And the a sub n itself, which is the leftmost number, would be, let's see why this is true. The other numbers can equal 0. See, it's on the line just above that. It says 0 is less than or equal to a sub I, but it's strictly less than b. That's what I was talking about. In base 10, the digits are strictly less than 10. In base 2, look back up over here where I wrote this number in base 2, notice that all the digits are less than 2, 1, 1, 0, 0, 1. In base 5 over here, when I wrote a number in base 5, look, all those digits, 3, 4, 1, 0, 2, are less than 5. And so in general, all the digits, a sub I, will be less than b, but some of them could be 0, such as in base 2 over here, and in base 5 over here, I have zeros there. So intermediate numbers can be 0, but the first number won't be 0. 0 will be strictly less than a sub n, which is also less than b. All the digits have to be less than the base. All the digits in base 10 have to be less than 10, up to 9. So let me just say something about that last inequality I just wrote. That simply says that the first digit isn't 0. Strictly speaking, it's not incorrect to, as a matter of fact, you've seen with computers nowadays, if you write a date, they want 2 digits for a date. So, for instance, if this is November 5th, so it might be written as 11/05/20, but ordinarily we don't do that. I certainly never do that. I mean, it is true, you could say that 0, 5 is, so this is 10 to the 0, the coefficient of 10 to the 0 in base 10 is the coefficient of 10 to the 1. So 0 times 10 to the 1 plus 5 times 10 to the 0th is 5. But for that matter, you could do this. This is also 5. It's 0 times 10 to the 2nd plus 0 times 10 to the 1st plus 5 times 10 to the 0th. And again, when I'm writing these numbers without subscripts, the base is understood to be 10. I mean, it's silly to do that. Is it mathematically wrong? Well, it's not mathematically wrong, but I hope no one would do that. There was a television program. I don't watch television, so I never saw it. But maybe in the 1960s, it was called 007. Well, first of all, that's not really right. O is a letter, the English name of a letter in the English alphabet, and 0 is a number. So it's not really 007, it would be 007. I never watched it. I don't know what it was about. I think it may have been some sort of detective program. But ordinarily, we don't write 007 if we mean 7. Just say 7. I mean, I think it's a little bit silly to write November 05, 2020. It's okay, so let's get rid of that and let's establish the theorem. Okay, so we're going to do this. Here, plan. Use our old friend, the division algorithm, to successively, one after another, divide the given number m and the successive quotients, that's the Q in the division algorithm, by the base B, which remember is more than 1. Let's observe that if B is more than 1, then if Q is positive, remember we saw at the beginning of the term, we can multiply both sides of an inequality, this inequality, by the same positive number and preserve the inequality. So we can write, I'll put the Q first. So multiplying both sides by Q. So if, for instance, M equals, say, Q, I'll just write, I'm going to use a subscript, but and M is positive, which it is in this theorem. So M would be greater than or equal to QB. Why is that? Since remainder R is, that's an R, since the remainder could be 0, but it's definitely less than the divisor b. So if m equals qb plus r, then m is at least qb. It might be more if r is more than 0, but r could be 0. And since, oh, here it is, since QB is greater than Q, so M is bigger than or equal to QB, but QB is strictly bigger than Q, and so M is strictly bigger than Q. The quotient upon dividing in the division algorithm by b greater than 0 is less than the number m that is being divided. So that's what we're observing. So if we keep on dividing by b, the quotients get smaller and smaller. We keep dividing, I'll say what we're dividing. I already said it, but I'll say it again. When we keep dividing the successive quotients by b, we get smaller and smaller quotients. But along the lines of Fermat's method of infinite descent, so all these Q's are positive. This process must come to an end. Look, all I'm saying, it's hard to write in general, but you know what I've just written perfectly well. If you take 28 and divide it by 4, the quotient is going to be less than 28. So each time you divide by a number more than 1, the quotient gets smaller. And then if you take that quotient, then divide it by that b, which is more than 1, the remaining quotient will be even less. And that process will come to an end because you have only a finite number of q's of quotients that you can go down to, because all the quotients are going to be positive, because m started out by being positive. So over here in this box, m is at least q times b. M is positive, b is positive, so q has to be positive. So let's do this. And again, don't be daunted by the notation. There are a lot of subscripts flying around. You have to keep track of them. But if you don't, as long as you have the general idea, I'm not going to ask you to write all these subscripts, but I would like you to see where it comes from, how we know that we can actually write a number. I mean, I'm sure it never occurred to you, in elementary school, you taught, how to read numbers, and it never occurs to you that, all the numbers, maybe it's mentioned occasionally, all the numbers, you can write any number, no matter how big, in base 10, using only 10 digits, stopping at 9. So let's show that we can always do that, not only with base 10, but with base b. So leave some room to the left of this. You'll see why. So here we go. M equals, let's say, q sub 1b plus a sub 0. And now we're going to take the q sub 1 that we had, that quotient, and divide it by b and get some quotient q sub 2 b plus some next number a sub 1. And now we'll take the this is go up to q sub 1. Q sub 1 equals q sub 2b plus a sub 1. So this is a 1. And so so now we have a quotient of q sub 2. We're going to take that q sub 2 and divide it by b, getting, say, some q sub 3 b plus a sub 2. And then you keep doing this. Eventually, you get to leave a couple of lines there. Eventually, you're going to get to, you can't keep making these q's smaller. So eventually, you're going to get to some q sub n where it no longer, where you can no longer divide q sub n by b. So it's like 0b plus some a sub n. So the one above that, that's where I left some room. So the subscripts on q, as you read down, are going up. So the one above it would be going down. So this would be q sub n minus 1 equals q sub. So look at the pattern that we have. Look at the top 3. For instance, the q sub 2 equals q sub 3. So the subscript on the new quotient is 1 higher, namely 3, than the q at the left. So this will be q sub 1 more than n minus 1 is q sub n b plus a sub, and then the subscript on a is the same as the subscript on q. Look over here, q sub 2, and then there's an a sub 2. So this will be a sub n minus 1, and the one above that will be, so I'm going up, so the subscripts are decreasing. So this will be q sub n minus 2, and then the subscript on the second q there would be 1 more than this n minus 2, and 1 more than n minus 2 is n minus 2 plus 1, which is q sub n minus 1. times b plus, and again, the subscript on A is the same as the subscript on the Q. It's n minus 2. Okay, so now we're going to, well, first of all, let's count these. So we started with M, and so going down, that's 1 step down, that's 2 steps down, dot, dot, dot. This is n minus 2 steps down. This is n minus 1 steps down, and this is n steps down. So there are n steps going down, so n steps going up. And so now what we're going to do is substitute back going up n steps from the bottom, which says that Q sub n equals A sub n. Okay, so when we do that, so okay, I won't well, okay, I'll rewrite it. Q sub n equals A sub n, and now we go up 1 step, which says Q sub n minus 1 equals Q sub n, but Q sub n equals A sub n. B plus A sub n minus 1. So that's what the second line up, which has Q sub n minus 1, it equals Q sub n, but from the bottom line, Q sub n equals A sub n, so it's A sub n, and then going back to the Q sub n minus 1, it's Q sub n, which is A sub n, times B, there's the B, plus, and then at the end we have A sub n minus 1. Let's go up again 1. So now we have Q sub n minus 2, right? And we have the third line up, Q sub n minus 2 equals what? Q sub n minus 1, but Q sub n minus 1 is A sub n B plus A sub n minus 1. But look at over here, Q sub n minus 2, it's Q sub n minus 1, which we had from the line just above this. Here's Q sub n minus 1. It equals A sub n B plus A sub n minus 1. But going back to Q sub n minus 2 here, look, Q sub n minus 1 is multiplied by B plus A sub n minus 2. So q sub n minus 2, if you distribute, if you multiply in this b, we get a sub n b to the second plus a sub n minus 1 b plus a sub n minus 2. And keep back substituting into the higher lines till you get back up to m. Well, so up here we have q sub 2. So eventually, when we keep doing this, we get q sub 2. Okay, so all these, look at the pattern, they all start with a sub n b, a sub n b squared. So this will take us back to, we're almost at the top here. So going back up, there are n steps. There are n steps going up. This up here, m is the nth step. This is the n minus first step. Q sub 2 is the n minus second step. And so that's going to be, just like the others, it starts with a sub n. And you get, so you've gone up, so q sub 2 is n minus 2 steps up. So you have a sub n b to the n minus 2 plus the next lower a times b to the n minus 3 plus, and this keeps on going till you get to a to the 2. Notice the subscript on the a, which is on the q, which is 2, is the same as the subscript on the last constant, just like in each of the others. The subscript on the q here, n minus 2, is the same as the subscript on the constant. Going up to q sub 1, we're on the way up to m. Want to see what m looks like. This one equals, so what's happening here? Each time we go back up, we started with, over here we have no b at all, it's b to the 0th. Here we have b to the 1st. Here we have b to the 2nd. So here we have a sub n b. So the exponent is increasing. Here the exponent of b is 0. Here the exponent on b is 1. Here the exponent on b is 2. So we increase the exponent from q sub 1 to q sub 2. So it's going to be b to the n minus 2 plus 1. You're increasing it to the n minus 1 plus, and then we have a sub n minus 2. And again, we're multiplying by b. So b to, make sure your subscripts look like subscripts, not coefficients. B to the n minus 2 plus, and this keeps going down. The exponent on b keeps going down till you get to a constant whose subscript 1 is the same as the subscript over here. And finally, in the last step, we get back up to m, which again starts with a sub n. The exponent on b increases, b to the nth plus a sub n minus, this should be n minus 1 over here. the subscript starts with n, and then a sub, again, the subscripts, a sub n b to the n minus 1 plus a sub n minus 1, right, b to the n minus 2, right, yeah, this is, let me make that clearer. This is a sub n minus 1, b to the n minus 2, and so on. And so next, we finally have a sub n b to the n plus a sub n minus 1 b to the n minus 1 plus a sub n minus 2 b to the n minus 2 plus, and this keeps on going until you get down to a sub 2 b to the 2 plus a sub 1 b to the 1 plus a sub 0 b to the 0th. And so we have shown that any positive number m can be written as a sum of constant coefficients, those are the a's, and with the exception of a sub n, all the other a's could be zero. They could all be zero, but the first one, again, you're not going to start out with a zero. So a sub n itself must be, as we said in the statement of the theorem, a sub n itself will be actually greater than zero, not equal to zero, because you don't start a number with zeros on the left. But all the others could, they have to be less than b, but any or all of them could be zeros. So for instance, in the decimal number 1000, the first digit is not zero, it's one, but all the other digits are zero. Now, that's okay. And so this, so that completes the proof that an integer greater than, well, positive number, a positive integer greater than zero can be written as a sum of products of non-negative powers of any base. We looked at base 5, we looked at base 2, base 10, of powers of any base b greater than 0, where all the coefficients, the a's, are less than the base b. Is it clear why? Take a look at what the a's are. The a's are remainders upon division by b, which is greater than 1. So remember the division algorithm, they are strictly not less than or equal to, but strictly less than the divisor B. So the A's, if you look at the box here, the A's are the coefficients and they're all less than B. And so that shows that in base B, we can express any number, M, as a sum of products of non-negative powers, could be zero power, of any base B greater than 1, where the coefficients, the A's, are less than base B because, as I just wrote, because the A's are the remainders when dividing by the positive number B. And so from the division algorithm, are less than B. So this proof not only proves that we can write any number in base B, but it also gives us a way of changing the bases. And so we'll conclude today by taking a look at this, how we can, well, we already saw how we can convert a number like up here, base 2, base 5, from a different base into base 10. You just write what it means. But what about, suppose you want to convert a decimal number. So I'll just conclude with this. To convert a decimal number to another base B, do what we just did in the proof. Namely, keep dividing by B. So we'll take one or two little examples of this and then call it a night, I guess. Keep dividing by B as long as you can, but eventually it comes to an end. And then read the digits of the resulting number, the number in the new base. Just the way we did over here. Look what we did. We worked back upwards. Look at what we got. We kept on dividing. We successively, wherever I wrote it, successively divided by B. We took the original number up here. We took the original number and divided by B, and we got a quotient. Then we took that quotient, Q sub 1, and we divided by B again. And we got A's, and then we took the next quotient and divided by b again. And we got another a. And we kept on doing that as long as we could until we got to the end and you could divide no further. And then look at what the digits are. Look at this box over here. The digits start where? At the bottom, a sub n times b to the nth, and then a sub n minus 1. So to get the digits of the new number in base b, we will read upwards. So the digits are a sub n minus 1, a sub n minus 2, and so on. So to convert a decimal to another base b, do we just did in the proof? Keep dividing by b as long as you can, and then read the digits of the number in the new base from bottom to top. So let's just conclude with a couple little examples. Right, let's say 27 in base 4. So we're going to start with 27. So usually if I want to divide, so I want to divide by the new base 4 into 27, I'd write it this way. But to facilitate its going like in the proof, I'm going to do it downwards. I'm going to write the division sign as it's sometimes done this way. So 4 into 27. So that is 13. And then keep track of the remainders, right? Because it's the remainders over here. The A's are remainders, and the A's are the digits of the number, the A sub n, and so on. So keep track of the remainders. So 2 into 27 is, I'm sorry, we're doing 4 into 27. So 4 into 27 is 6, remainder 3. Divide again. 2 into 6 is 3, remainder, wait, we're doing 4. We'll do one with a binary system. So 4 into 27 is 6 with a remainder of 3. So we divide by 4 again. We successively divide by the new base. We keep on dividing by the new base, 4. So 4 into 6 is 1, remainder 2. Now we do 4 into 1 is 0, remainder 1, right? When you divide 4 into 1, you get 0, but there's a remainder of 1. And so now we read up. And the answer is 27 base 10 equals 1, 2, 3, and you have to write base 4. Again, that's not 123, it's 1, 2, 3, base 4. How do you check it? The way we did before. 1, 2, 3, base 4. So this tells the number of 4 to the zeros. This tells the number of 4 to the ones. This tells the number of 4 to the twos. So 1, 2, 3, base 4 is 1 times 4 to the 2 plus 2 times 4 to the 1 plus 3 times 4 to the zeroth, which indeed is 16 plus 8 plus 3, which is 27. Let's do, let's actually, let's do 27. Let's write 27 in base 2. So your expectation is that there'll be at least 3 digits because you're using a smaller base. And when we did base 4, we got 3 digits over here, 1, 2, 3. So we're guessing that there should certainly be at least 3, if not more. So how do we do it? We start with the number and we successively divide by the new base 2. And we keep track of, as we go along, we keep track of the remainders. So 2 into 27 is 13, but there's a remainder of 1. Well, divide by 2 again. 2 into 13 is 6, but there's a remainder of 1. Divide by 2 again. 2 into 6 is 3, and that goes in exactly, so the remainder is 0. Keep dividing by 2 until you can no longer do it. 2 into 3 is 1 with a remainder of 1. Keep doing it. 2 into 1 is 0. Okay, so that was that bottom line in the proof, 0 with a remainder of 1. And so read upwards. And so we see that 27 base 10 equals, so we're starting at the bottom and we are reading upwards, 1, 1, 0, 1, 1, and then you have to write base 2. And so as you expected, when we did it in base 4, we got 3 digits, but when we used a smaller base, we needed more digits. We needed 5 digits, for obvious reasons. The base is smaller. And again, to check this, this is the number of 2 to the zeros. This is the number of 2 to the ones. This is the number of 2 to the twos. This is the number of 2 to the threes. This is the number of 2 to the fours. So check. We get 2 to the 4, 1 times 2 to the 4, plus 1 times 2 to the 3, plus 0 times 2 to the 2, plus 2 to the 1, plus 1. So 2 to the 4th is 2 times 2 times 2 times 2 is 16, plus 2 to the 3rd is 8, plus 2 squared is 4, plus 1. 8 and 16 is 24. Wait, 0 times 2 to the 4th is 16, plus 2 to the 3rd, but 0 times 2 to the 2nd, plus 2 to the 1st is 2, plus 1. So it's 24, 25, 26, 27. Yeah, equals 27. So let me come back to you and just say a few words. So let's end this.
The recording has stopped.
Okay, the recording has stopped, and some of you managed to still be there. Very good. Let's see how many. 27. All right. Okay, so why don't you make up a few examples like that? They're easy enough. And again, I apologize for a proof that looked harder than it really is. It's just repeatedly dividing by the new base. And so what I would like you to do, or what I would like me to do over the weekend is finally get to where I'm making more progress on this. And what I would like you to do over the weekend is make up some examples and change bases and, write 120, 129 in base 5 and base 6 and base 4, and also continue working on the sheet that starts with the Diophantine equations and do the 5 questions. There are 5 questions at the bottom. After class, one of you asked about 2 of them on Tuesday. I would like you all to work on them. They use the fundamental theorem of arithmetic and the idea of unique factorization, and it gives you an idea of what you can do with unique factorization and